All right, so in solving this problem, we got to write the equation. And writing the equation goes back to those notes you took yesterday. The first thing we write is we write a of t. Now, I know that I actually know the amount of time in this problem, so I'm going to go ahead and fill that in right now. So it's going to be a of what? Well, notice we get this investment when we turn 18. We want to see what it's worth when we turn 60. How many years is that? 42. That's what we have to know, is that it's going to be 42 years. All right, so a of t equals p. P's principal. What's our principal value here? Yep, it's 1,000. Because remember, principal just means starting value. It's what we start with. So it's going to be 1,000 times 1 plus r. What's r here? Yep, 0.11, absolutely. Now, if you don't remember how to get the r value, it's the original percent that we start with divided by 100. Because we've got to turn that percent into a decimal. All right, last thing in our equation, it's got to be to the power of t. We already know what t is. It's going to be to the power of 42. Now, if you didn't get that equation, now you have it. Everybody should now be able to go and find out what that final answer is if you haven't gotten it yet. So when you're evaluating this, I would definitely suggest you actually write down what that addition gives us. I'll sometimes see people who will try to type it in from the original, complete with the parentheses and everything. And while that does technically work, it's also prone to errors. We forget a parenthesis or we don't put something in the right place. It's much easier and more reliable to just do the 1 plus 0.11 and then worry about doing the work. And when doing the work, remember exponents first. So 1.11 to the power of 42, then multiply that by the 1,000. And again, you notice I gave 2 decimals here. Why is it 2 decimals? Because we're talking about money, absolutely. Every time we're talking about money, I don't have to tell you what to round to. You should already know, by default, give me to the nearest cent. All right, now, before we go on and extend this problem just a little bit further, I want to make sure that you really get what's going on here, because this is compounding interest. And if you really get the power of compounding interest, it's going to help you a lot for the future. Because let's look and see what happened at both ends of this problem. Going from year 0 to year 1, we started with $1,000, and we earned 11% of that as interest. So that's just over $100. So first year, we earned about $100. In order to get from year 41 to year 42, in order to get this amount, in interest alone, we earned about $8,000 in order to be able to get to this number from year 41. So in the first year, you earn about $100. Year 42, you've earned $8,000 just in that 1 year to get us up to $80,000. That's how compounding interest can be so useful, because if you let it grow big enough, you're making quite a bit of money just from the interest. Now, to extend this same problem out a little bit, I want you to consider this scenario. What if this ant, and of course I hope that you all have such an ant, wouldn't that be nice, right? What if this ant gave us this $1,000 when we were born instead of when we were 18? We still want to know how much is in there when we turn to be 60 years old. Please calculate the new value based on this situation, getting it when you're born instead of just when you turn 18. So in this problem, we still are starting with the same basic equation. We still have the same principal. We still have the same rate of increase of 11%. The only thing that's changing is the amount of time. Now in this problem, what is the value of t going to be? 60. It is 60, yeah. So this is what we're calculating. So you're going to do 1.11 to the power of 60, get that value, multiply it by 1,000. If all goes well, you should be getting this number, $524,057.24. That's not bad for $1,000, right? And again, let me go back to that point that I was making earlier. Year 1, we made $100 or so. Year 42, you made about $8,000 that year in interest. Year 60, You made about $50,000 that year just by letting that investment grow. You didn't have to do any work in year 60 in order to make that happen. But I do want to make something clear, the little bit of real world application on this. You don't have to do any work in the year 60 to get there, but you do have to do a lot of work to get to that point, because it's actually one of the hardest things you can do. In order to let it get to that point, you have to have left it alone, which is really hard at that time. Somebody gives you $1,000, you have to make the choice, I'm going to invest it and I'm going to leave it there, instead of buying a phone or whatever else may be on your radar at the time. That's the hard part, putting it in and then forgetting about it. Just leave it there, don't mess with it, and if you don't mess with it, this is what happens. We're now going to take a little bit of a shift sideways, and we're going to come back to this tomorrow, but for today, we're going to be doing a little bit of graphing. In fact, we're going to see how to graph a new function type. For doing the graphing, we're going to need today 2 graphing grids. So please set up 2 graphing grids on your own paper so that you're ready to roll here in a moment. Before we start learning our new graph for today, I'd like you please to start with something that you know already that's going to be closely related. Please start by graphing this, y equals 2 to the power of x plus 1. Make that graph complete on your first graphing grid, please. All right, so first up here, a little bit of quick background information. Where's the asymptote going to be? Well, you notice that this one's been shifted up 1. And so our horizontal asymptote that we have with an exponential is at y equals 1. A little bit of a reminder, just kind of good information for us to keep in mind. Domain and range. The domain is all real numbers because it goes forever left and right. Range, is it going to be above or below the asymptote? Above. Therefore, our range is y is greater than 1 because it's above the asymptote. And so then I start graphing it with that stuff in mind. First thing, draw the dotted line in for the asymptote there at 1. Then having done that, our first point. Remember that the first point starts up 1. Nothing's changing that in this problem. So we start up 1 from the asymptote, and then this is 2 to the x. 2 to the x means double that height as you go to the right. So 1 goes to 2, 2 goes to 4, 4 goes to 8. If I'm multiplying by 2 on the right side, what am I doing on the left side? Dividing by 2, yeah. So I divide by 2 on the left side, put at least 2 of those points in. And then once you've drawn at least 2 of those points on that fractional side, you can draw on the curve. Make sure you have that written down and drawn correctly on your graphing grid, because we're about to use that to make another graph. We are going to be looking at what the inverse of an exponential is. And so on your paper, have some space where you can do the algebra. And we're going to figure out what the inverse equation is first of y equals 2 to the x plus 1. And then we're going to look at what the graph of that would be. So, what's the first step in finding the inverse equation? Yeah, many of you already got it, right? Switch x and y. So we start by switching the x and y's places. So now we have x equals 2 to the y plus 1. And now we look at what we have in order to figure out what strategy we want to use for solving it. I'm going to try to solve it for y. Y is in the exponent. I solve for an exponent by turning it into a logarithm. But I can't do that yet, because you notice I don't have the exponential part by itself yet. I have to get that part by itself. So first step from here, subtract 1 from both sides. That then gives us the exponential by itself. That gives us the 2 to the y equals. That's going to allow me to actually solve it from there. And of course, make sure you're getting this down on your paper as we go, so you have a correct version. All right, so now that I have the exponential part by itself, in order to solve it for y, I can turn it into a logarithm. And so when we turn it into a logarithm, remember, logs exist for the sake of solving for the exponent, so log equals the exponent. So we get log base 2 of x minus 1 because it's log base 2 of whatever the original equaled. So since the original equaled x minus 1, that's what has to be in there. And make sure you have the parentheses around it because that's going to change what that 1 does. We're now going to graph it. Now we have never graphed log base 2 of anything before. And so that's why I had you start with the y equals 2 to the x plus 1. Since this is the inverse of that, I can graph it by using the original graph. What do I do to the points to find the inverse? Yep, exactly. We switch the x and the y coordinates. So for instance, my original graph, I started by plotting the point 0, 2. Well, if I switch the x and y coordinates then, that gives me 2, 0. So that's going to be a point on this graph. I can do the same with every single other point there. So for instance, 1, 3 was the next point that I plotted. If I switch the x and y, 3, 1. Okay, next up. I'm going to take that point and switch the x and the y coordinates. So this point's at 2, 5. So on the inverse, we have 5, 2. Okay, what about this point? The last point that we plotted on the way up. What are the coordinates? Switch the x and y. 3, 9 is going to become 9, 3. You can do that with every single point that we plotted in the original.
I just don't understand why you could go below.
Now, as you take a look at that graph, it looks like it's crossing through the asymptote, right? We can't ever cross the asymptote. That's because that's the asymptote from the original. That's not the asymptote of this graph. We are graphing both on the same set of axes, so it could look a little bit mixed up there at first. But we got to do it on the same set of axes for the first time just so we can see what happens with logs. All right, now one other thing that I plotted on this, I want to draw your attention to here. This point down here. Well, I wanted to know what was happening outside of this. So I went over here and grabbed this point, negative 10, 1. If I switch those coordinates, I end up at 1, negative 10. That tells me then that as I draw my curve in, that's where it's flattening out. And by looking at this graph, can you now see where the asymptote should be? Notice it's a little different this time. The last problem with our exponential, we have a horizontal asymptote. In this case, though, it's flattening out along here. Therefore, it's a vertical asymptote that goes through x equals 1. Please get that down. We're going to be able to practice it here in a minute, but first I want to make sure that you have it correctly down your paper. Now that we see what the graph looks like, I want to just now isolate that log graph and figure out some characteristics of it. So where's the asymptote then? How would I actually write the asymptote? If it's vertical, is it x equals or y equals? Yep. It's x equals 1 for the asymptote here. What will the domain of this be? Well, first of all, is the domain of the log graph, is it all real numbers? No. Because you'll notice there's no graph to the left of the asymptote. It's only to the right of the asymptote. So our x values start at 1, and they get bigger from there. So our domain is x is greater than 1. Okay, what about the range? Is the range all real numbers? Yes. Yes, it is. Because it certainly is going down forever. That's a bit easier to see normally. But it's also going up forever. Yes, it's kind of flattening out, but it continues going up. It always is going up there. So, taking a look at that log graph, a few things to note here. First of all, a logarithm graph is always going to have a vertical asymptote instead of a horizontal one. Because it's a vertical asymptote, it's going to change when we shift it left and right.
Should we write this down?
Okay. Also, notice what's happening and how we can actually make this graph. The distance from the asymptote is multiplied by the base as y is increasing. This is the same idea as with an exponential, but it's just been slightly tweaked. Because I start over 1. The exponential started up 1. This one starts over 1. After I go over 1, I've gone over 2, then over 4, then over 8. So notice as I'm going up, I'm doubling the distance from the asymptote. I'm doubling it because this is log base 2. Next up, we're going to see how do we then graph it straight from the equation. So please write this equation down above your second graphing grid, and then we're going to graph this. So first thing we're going to figure out about this is just what is the parent function, and then where does that mean the asymptote is. So first of all, the parent function, remember, is what we're left with after we take away any transformations. And in this case, the plus 4 and the plus 2 both represent transformations because they're adding or subtracting within there. So notice what that leaves behind for our parent function. Our parent function here is y equals log base 3 of x. Just like an exponential could be 2 to the x or 3 to the x, it's just some number to the x. A logarithm parent function is log base something of x. Now then, the transformations then that are involved. The plus 4. Which way does the plus 4 move it? Up, down, left, or right? Left. Yeah, it's left, because it's in with x, so that already tells me left or right. And between left and right, plus goes left. So then what's the plus 2 do? It goes up 2. Because the plus 2 is hanging on the end. It's not in with the x, so therefore it moves it up and down. Knowing that, where is the asymptote? Well, first of all, which way is the asymptote going here? Is it horizontal or vertical? Because oftentimes we're so trapped into the exponential mindset that we forget that this one's a vertical asymptote now. Now, if I take a vertical line and I move it up, isn't it still in the same place? But if I move it over, then it changes. So my asymptote is moving left 4 here. So that means my asymptote is going to be written as x equals negative 4. And when you have that in mind, then we start graphing it kind of the same way that we started graphing with our exponentials. Step 1, draw the asymptote. So do so. Having drawn in that asymptote, then it's a matter of where does our first point go? Well, normally our first point for a logarithm goes right 1. But in this case, it is being changed. Where am I moving this point? Up 2. So that means that my first point is up 2. It's still over 1. Nothing changed the over 1 from the asymptote, but it's up 2 from where it normally would be. Now that I've plotted my first point, I've used the plus 4. I've used the 2. So the only other number I have to worry about in doing this whole problem is the 3. That's all that I have to worry about now. And the 3 tells me what I'm multiplying my distance from the asymptote by. So our first point's 1 away. My second point then is going to be 1 times 3. It's 3 away. So as the y increases, or in other words, as we go up, I'm multiplying the distance from the asymptote by 3. So I went over 1. 1 times 3 was 3. How far am I going to go over next? Well, it's going to be 3 times 3.
9.
Yep. So it's over 9 next. And again, make sure you're counting from the asymptote. Just like you do with an exponential, you're counting from the asymptote. Now, as I'm going up, I'm multiplying by 3. So then, what's going on as you go down? We're dividing it by 3, yeah. So 1 divided by 3, that's a third. So I'm only 1/3 over from the asymptote. Okay. If I go down again, I'm going to be over just a third of that third, which you can do visually, technically speaking, that is at 1/9. Remember, I still want you to include at least 2 of the fractional values because it tells you where the shape of the graph is going to be going. But since you have those points and you have the asymptote drawn, you can draw the curve in now. And that's how you graph logarithm. It's just like an exponential, except it's on its side, basically. So last thing, what about the domain and range? Okay, the domain. Is our domain on this problem all real numbers? No, it's not, because it doesn't go to the left of the asymptote. So instead, for our domain, we're going to say that it includes all x values that are to the right of the asymptote. So that means x is greater than -4. And the range? Is the range all real numbers? Yes, it is. The range here is all real numbers because it goes up forever and it goes down forever.